Okay, so in this hour, I was going to say a little bit more about hybrid programming with MPI and OpenMP. Honestly, I won't have too much to add beyond what Bill's already talked about, but I'll try to add a little more, maybe a little more from the OpenMP perspective. But some of it might be kind of repeating, and I'll try to skip through a little quickly through those particular parts. And then after that, I'm going to talk about just some practical matters with using OpenMP, so some common programming errors, some common pitfalls that you might encounter when you're using OpenMP and you're programming with it, and also a few miscellaneous performance topics. So we kind of touched on some of that stuff in the morning, and I'll just elaborate a little more on that. So as you know, systems today, they are essentially hybrid architectures in the sense that typically you're going to have an SMP cluster where you have nodes which are connected together, and then within the nodes you have an SMP, and then there's a variety of different architecture layouts of the cores and so forth within the SMP nodes. So there's different ways you can program this. So as Bill had mentioned, one of the most common ways is doing MPI plus something, and OpenMP is often that something. So we can kind of come up with like three general approaches that are very commonly in use. Pure MPI, which is where each core runs an MPI process. And you could do this, you could do MPI everywhere, so all the individual cores on the SMP nodes are also each running MPI processes. And for certain types of applications, this works actually really well for the reasons that Bill had mentioned. If you have codes that are very regular and where locality management is really important, MPI can work really well for you there. There's also support in MPI 3 for shared memory. So that makes a sort of hybrid-like model where you're combining different ways in which you can use MPI together. That's actually a viable way of doing a hybrid-like programming. And for more details on that, you can look at that paper that I cite down there. It talks about that kind of hybrid programming model. The pure OpenMP, OpenMP obviously is used quite a lot for just shared memory programming. And it's also been used on some larger scale shared memory systems, on some CC/NUMA systems. Trying to scale that out well beyond that, for instance, in a cluster environment, has generally not worked all that well. It tends to not be very scalable, though there have been some approaches to trying to use like some sort of virtualized layers, a distributed shared address space layer, where you can try to get OpenMP to run in that sort of environment. But it generally has not, that's not usually an option that most people go to. And then, of course, you have MPI plus OpenMP, and that's what I'm going to talk a little bit more about. And with this option, you can kind of distinguish two different approaches. One is, I can call it like a non-overlapped approach, or it's sometimes called a master-only approach. And here you have a master thread, which is making all the MPI calls, and no other threads are intended to be active. Right? So it's not quite the same thing as the MPI thread single or the MPI thread funnel. It's something sort of like in between, where the idea is only a master thread is making the MPI calls, and no other threads can actually be running at the same time. But in this mode, it does permit you, for example, to make MPI calls, and then you have separate parallel regions where there aren't any MPI calls whatsoever being made in those parallel regions. And this is a very common way in which people have incorporated OpenMP into their MPI programs by using this approach. So you have an existing MPI code, and then you just find, as an example, loops in your code that you can just parallelize. And that's one way in which you could try to incorporate OpenMP into your program. And the other approach, maybe a little more interesting, is what I'll just call an overlapped approach, where you can have MPI, and while MPI calls are being made, you can simultaneously have other threads doing other things. And the other threads could be themselves making MPI calls, or they could just be doing other useful work while the master thread or some other thread is busy doing some MPI things. And there's a lot of different ways in which you can exploit this approach. OK, so what are some reasons why it might be a good idea to add OpenMP into your MPI program? Well, one thing is that OpenMP oftentimes can be a much more efficient way of programming on intranode systems. And by efficient, mainly what I'm talking about is memory usage. So for certain types of applications with MPI processes, you're replicating your data structures in such a way where there's actually, for instance, if you're decomposing your data and you're doing some sort of like Halo exchange type updates, your duplicate, there's extra memory that's being allocated at each process to do those halo exchanges. So if you decompose it to a certain extent, the amount of your data that's just being consumed just by these ghost cells, they tend to increase dramatically. And within the node, that can result in lots of memory being used. And so it might be more effective to use a shared memory approach like OpenMP or pthreads, for example, in order to lessen the amount of memory that's being used. For fine-grained parallelism, it might be more effective to do that via shared memory rather than going through the MPI software stack when you're trying to communicate between different threads or different processes. And then it's possible also that if you wanted to use OpenMP within the node, you have to ask the question, do you want to use OpenMP everywhere? So for example, you have one MPI process, and you have a bunch of OpenMP threads. Or rather, would you observe that within the node, you have these so-called NUMA domains, and maybe you have one MPI process per NUMA domain, and then you have each process is supplemented by a set of threads. So there's different arrangements you can do there, but this is another consideration to think about. Another aspect for why you might want to add OpenMP is there might just be certain constraints on the total number of MPI processes that you can use in your application. So again, you might have certain per node memory limits. And in particular, as Bill had mentioned, as you're increasing, as these nodes the core counts are increasing, there's also the per core, the amount of memory you have is also decreasing. So this is a constraint which could limit how many MPI processes you could feasibly use on a particular node. And there might be other limits that are imposed, for instance, by the system. You only allow a certain number of MPI processes. Or maybe the application, sort of thinking about something about the algorithm of the application, it really only makes sense to use up to a certain number of MPI processes. And if you want to scale past that, you need some other option, like using threads, for example. And then another reason, some applications, it might exhibit some sort of hierarchical parallelization pattern. So that might be within the algorithm itself, that it might naturally decompose into two levels. So where in that situation, it might make sense to use MPI at the top level and then something else like OpenMP, for example, at the second level. And that might be a very reasonable approach, and it might make sense algorithmically. And then finally, and this is really important, if you have an application where your workloads are unbalanced, then making use of threads to help balance those workloads, that can actually make a big difference. And I'll go through a brief example where you can actually see how that's demonstrated. OK, so there's some reasons to use OpenMP, but there's also some reasons why you want to be cautious and why it may not be a good idea. One thing is interoperability issues between MPI and OpenMP. Does the MPI library actually, what level of thread safety does it guarantee? Now, I think many of the MPI implementations that are in use now, they do provide good levels of thread safety all the way up to the MPI thread multiple, but then you're going to have potentially a performance impact there as well in order to give you that level of thread safety. So this is one thing to consider. And then also just the added complexity in the program. So we mentioned in the morning that there's some various issues that you have to consider when you're dealing with shared memory programming. Things like data races is something that can come up, or even other issues like false sharing, which I'm going to talk about a little later. So all these issues that are related to shared memory programming, you also have to account for that in your MPI application if you're combining these things together. So that's an added level of complexity you have to contend with. And then finally, if you're limiting the amount of communication to a single thread, are you actually able to saturate your network port? Are you really being able to exploit the bandwidth that's available to you? So if you don't have say n number of processes that are communicating, you're restricting that to just one, and then using threads everywhere else. Are you really exploiting the network resources that are available to you? So this could also be a consideration for why you may not want to use OpenMP. At least not OpenMP everywhere, and just using one MPI process. So I had alluded to this a little earlier. So on the nodes, there's various types of configurations you have to deal with. It's not just different network topologies between nodes, but also within the nodes, you have different topologies in how the cores are laid out, how the sockets and the cores and all these things are kind of come together. And so there's a lot of decisions that have to be made on how you would actually apportion the MPI processes versus the threads. And these can have dramatic impacts on performance too. So that's the only point I want to make here. So there's different arrangements you could do. And resource utilization considerations, again, I sort of alluded to this already, but one aspect is network utilization. So if you only have one MPI process per node, are you able to saturate the network port? And sometimes you can do that. Even with a single thread, you're able to do it. But if you have multiple network ports that are available in the node, if that in particular becomes commonplace in the future, then this might be something that you would actually want to have multiple MPI threads or processes that are doing the communication. So this is something to consider. Core utilization. So introducing threads into your MPI application could help you in some ways in terms of core utilization, but there can also be some drawbacks. So one way in which it can help is if you're doing communication and you're not able to achieve a certain level of overlap, computation communication, well, introducing threads might allow you to get some extra overlap. You might be able to keep other cores busy that otherwise wouldn't be able to, that you wouldn't be able to keep it as busy. And then also, if you have unbalanced workloads, introducing threads might help balance it in a certain way, and then again, that can also help in terms of core utilization. On the other hand, if you're using this master-only approach, and then you have a number of other threads, but while the MPI process that's running and making MPI calls is in the MPI library, the other threads are say sleeping, then this is going to limit your core utilization, right? This is a situation where you're not actually taking advantage of all the cores on the system. So in practice, when you're doing hybrid programming, typical way you would start is generally you would start with an MPI application. You already have your MPI program, and then you're trying to figure out what's the right way to introduce OpenMP into there. And one of the first things you would look at probably is loop parallelism, right? So within each MPI process, there's presumably a number of loops. Loops tend to dominate the codes we work with. And so you can try to see if there's opportunities where you can just quickly add OpenMP, and then you can gain some additional benefit that way. And then there's other things you can also look at. Can we exploit task parallelism? With OpenMP 4.0, which is going to be coming up, the talk, we're going to talk also about using accelerators or SIMD directives. So these can also be incorporated potentially. And those offers other ways to hybridize your applications. In terms of strategies, there's different considerations. So this is a very complicated problem, how you go about actually writing your hybrid applications and getting the exact configuration that works the best for your application and your platform. So this is just covering different things you have to think about. Varying the number of threads based on the workload in each process, finding the right mapping of threads to cores, how you can best exploit threads to overlap computation with MPI calls in order to prevent blocking in the MPI library if that's what you're observing. And then there's lots of experimentation to be required, figuring out what's the right combination of threads and processes, and then also thread affinity. So it was mentioned how process and thread affinity and also memory affinity, all these are critical performance factors. So when you're introducing an additional programming model, this sort of exacerbates that issue of figuring out how to place the different processes and also the different threads and how they're going to interact with each other. So this is, again, just recapping already what was said in the previous talk. MPI now supports these 4 basic thread support modes. So with MPI thread single, you assume that the process is not multi-threaded at all. So you only have one thread that's making MPI calls. Funneled will allow a multi-threaded process, but there's going to be one designated thread which is making the MPI calls, and no other thread can make any MPI calls. Thread serialized means that it's multi-threaded, and multiple threads can make the calls, but they can only do it one at a time. The calls are serialized. And then finally, you have thread multiple, which is a free-for-all. Any number of threads can be making MPI calls, and they can be making them simultaneously. So just a few code examples just to illustrate the idea. Though I think you probably already got it, but just to illustrate what it would look like. So you would replace your call to MPI init with MPI init thread. And then, for instance, if you're using funneled, you could specify that you want MPI thread funneled, and then you would it would return back to you what level of thread support the library is going to give you. And then with this particular mode, what you could do is you could have a parallel region, and then within the parallel region, you could use for instance, a master construct. You can use the master construct, which means the master thread is going to execute that particular code block inside that construct, and it can be doing MPI calls. And then and then the other threads could then be doing some other work, but the other threads cannot be doing any MPI calls whatsoever. So that's what Funnel will allow you to do. With serialized, it offers a little more flexibility. So now you can have MPI calls in your parallel region. Again, they must be serialized, so they would have to be in some sort of like single construct, for example. But any threads can execute it. So you could have, you're not restricting just to one particular thread. You could have any number of threads that actually can make those MPI calls. There's a potential performance penalty that comes with that, which Bill mentioned, where whenever you have different threads or being able to make MPI calls, that can have issues in terms of the memory access. But this can offer some more flexibility in your codes. Okay, and then you have MPI thread multiple, which again, as I mentioned, this just means any of the threads can be doing communication. So you can have all the threads in your thread team all doing MPI send and receive. So here, for example, threads with the same thread ID are doing send and receive, and they're communicating with each other on different MPI ranks. Okay, so one of the ways that I had mentioned before about how we can utilize OpenMP in your MPI programs is to try to hide some of the communication latencies. So one thing to keep in mind with MPI communication is, it offers non-blocking and blocking calls, but oftentimes the non-blocking calls really are blocking in the library to some degree. And because oftentimes to actually get progress, it requires another call into the MPI library. There can be, on some platforms, there might be some hardware support to enable some progress in the background, or maybe some helper threads might be used, but oftentimes that's not actually available. So under this scenario, we can utilize OpenMP potentially to help actually get more of this in order to get more work done while this communication is going on. And there's different ways in which we can use OpenMP to achieve that purpose. So I'm just describing a few different ways in which you can use OpenMP to try to hide some of that latency here. So one is, which I'll just call an SPMD approach. And by that, what I mean is that you can have a parallel region, and then each of the threads in the parallel region, you kind of decompose them into sort of like subteams where each different sets of threads are going to be doing different pieces of work. So you might have, for example, the first thread doing some MPI stuff, and then all the other threads might go on and do something else. And this would be legal if you were doing, for example, MPI funneled. It would allow you to do something like this. The issue, though, is these other threads that go on to do something else while the first thread is making an MPI call, there's certain limitations on what those other threads can do, right? So for example, you wouldn't be able to make use of work sharing constructs in this else block because the work sharing constructs require that all the threads participate. So using this sort of style wouldn't work. Of course, you could manually write the code in such a way where you can divvy up the work you're trying to do amongst the remaining threads, and you could do that. But that would require more programming effort and isn't really the OpenMP style that's encouraged. So this approach might be somewhat cumbersome to actually make use of in practice. Instead, what you could do is you could use nested parallelism. Again, you have to check if your implementation actually supports it. I think generally most OpenMP implementations will support it. By default, it wouldn't be turned on, so you'd have to explicitly specify that you want OMP nested parallelism to be true. So OMP nested equals true. You can set that environment variable, or you can make a runtime library call to set the nested mode. And then once you've done that, what you could potentially do is you could have a parallel region with, say, 2 threads. And then one of the threads is, again, doing some MPI calls. And then the other thread will go on, and then it'll spawn its own parallel region with a certain number of threads. And then now those threads can actually do work as a team, you can execute work sharing constructs and so forth, while this first master thread in the upper level team was doing the MPI stuff. So this is one way in which you could do it using nested parallel region. Another way that could work is making use of this no-wait clause. You could do something like the following. You could have, say, the master thread make calls into the MPI library. And then the other threads will continue on. Remember that with master, unlike with single, there's no implicit barrier at the end. So while the first thread is executing this portion, the remaining threads will skip around and then continue executing. And so the other threads can, for instance, enter into an OMP4. And if you notice, I put a no wait here. So what that means is that these threads can start executing this parallel loop, and they can start doing work. And they can, once they finish their portion of the iterations that they got for this loop, they can continue on to the next loop even. And then eventually, once this first thread finishes doing whatever it needs to do here, it can go in and then it can add its contribution to complete these loops. So that could be another way in which you can go about doing it. Finally, I wanted to just mention one other approach, which is making use of tasks, which we learned about in the morning session. So here, what you could do is you can have a master block. And then what this means, again, is that the master thread is going to come into here, and all the other threads will skip around, and they'll hit the barrier. While the other threads are waiting in the barrier, the master thread will come, and then it can generate a number of tasks within a loop. So this is a very common pattern when you're dealing with explicit tasks in OpenMP, is you have one thread in a loop generating a bunch of tasks. And again, if you recall, with tasks, when you generate a task, you're not executing it yourself, but rather what you're doing is you're creating the task, and it's going into a pool, into some sort of task pool that the OpenMP runtime is going to manage. And those tasks can be picked up by any of the other threads in the team. So as these other threads are waiting at the barrier, the master is creating a bunch of tasks. And as these tasks are being added into the pool, these threads here can go and they can pick up the work. Okay? So the master just generates all the tasks that it wants to be able to do. And then once it does that, it can execute the MPI call. So that could be another way of doing it. Are there any questions with these examples? Yeah?
I'm just curious, so what if the work that you do in the threads
are dependent? Yeah, exactly. So yeah, all these examples here, I was assuming that the work you're trying to overlap with the communication is independent. Yeah. So you would have to be careful about that, obviously. Yeah. So in this case, I'm presuming that all this work is independent of what's going on here. And then how can we just, if you happen to have other work that you can do side by side, what are different ways in which you can go about doing that? Okay. So I just wanted to go through one quick example. I'm not going to go into detail on it, but just to illustrate two cases, one where this adding OpenMP to MPI worked well and where it didn't work particularly well. So both of these cases can be found in the NAS multi-zone parallel benchmarks. And there's three benchmarks that come with this, LU, SP, and BT multi-zone versions. And these are used to compute solutions to these compressible Navier-Stokes equations, and they're used for doing CFD simulations. And the way these benchmarks work is, a bunch of zones are set up which are dealing with different mesh sizes potentially. In the case of BT, for example, the different zones have dramatically different sizes. For SP, the zones tend to be more equally sized. And so what will happen is these zones get set up, and you can execute it using either all MPI processes, so in which case each zone might go to a particular MPI process, or you could make it so that you have a set of zones going to a particular process, and you can have some threads. The process itself can be multi-threaded, and it can be working on the zones. And the question is, which approach works better? So, these benchmarks have been studied quite a lot in the context of trying to understand these hybrid MPI and OpenMP programming model. So one particular look at it recently found, and this was on the Ranger supercomputer at TAC, and it found in particular that for BT, which exhibited this very unbalanced workload for this particular benchmark, that you could get very good performance improvement by employing OpenMP instead of just using pure MPI. So as an example here, you can see if you're just comparing the light blue with the dark blue, you can see how much better performance in terms of flops per second that we were able to get using the hybrid version. So, and the reason again for this is that for this code, the zones were very much not equally sized, so it was very unbalanced. So with MPI, what happened was, for instance, if you went up to 4096, well, at this problem size, there's a total of 4096 zones. And the zones themselves are very much not, very different sizes. So you have a huge amount of imbalance going on there. So that limited performance. Whereas if instead you reduced the number of MPI processes, but you made them multi-threaded, then what you can do is you can assign to each MPI process, you assign a set of zones to them, a subset of the zones. And then you just have all the threads under that MPI process work on the zones simultaneously. And then that can even out the imbalance dramatically, and then that can lead to some major improvements. In contrast with the SP, where there was actually very little imbalance in the zones, you don't see much advantage at all by going from MPI to OpenMP. Yeah.
When you have a subset of zones for MPI process, if the total aggregate of that subset or subset is still unbalanced, because essentially the problem is coming because of load balancing or load unbalance. If there are 10 MPI processes and one of them has a huge amount of load because it got the subset of zones that it got were all big, then you essentially still have the same problem. I mean, even with MPI plus OpenMP, you will have a performance, degradation.
Well, okay, let's consider an example where, let's suppose that we had, let's just say just to simplify it, let's say we had two zones. One zone takes 20 time units, and the other zone takes 2 time units. I'm just taking an extreme example. So if you're executing that with 2 MPI processes, one MPI process would take the 20, the other would take the 2. And so the total time would take 20. If instead you did it with 1 MPI process and 2 threads, then the first one, the 20, it can be split between the 2 threads and take 10, plus the next one, again split between the 2 threads, 1. So you reduced from 20 to 11. I
mean, you still have, the ratio is still about 10, right?
But the total time, instead of executing each zone by 2 different processes, and then the one that's taking the longest time is.
You're assuming that for the first time you had only 2 workers.
Yes.
2 MPI processes. Next time, in the next case, you have 4.
No. In the second case, I'm assuming 1 MPI process and 2 threads.
Yes. So you have 2.
So in both cases, there's a total of 2 workers.
Yes. You have 2 computing units, right?
Yes. So in the second case, by using threads, you're able to distribute the work between the threads, whereas in the first case, one process had to take the larger zone, and the other process had to take the smaller zone. Whereas in the second case, you have 2 threads where both threads are working on the zone simultaneously, and so you're able to balance the workload between the threads. Does that make sense? And then in addition to that, you could also experiment with, if you have certain processes getting larger sizes, you could experiment with using more threads on that process versus another one. You could spawn extra threads to work on it. But just even if you didn't do that, you could still achieve a more balanced.
Let me ask something else.
Sure.
So when we are doing, or for this example, when we did MPI plus OpenMP, did we, so we reduced the number of MPI processes.
Yes.
And added more threads on each MPI process. Did we put a lot of zones on one MPI process? Or did we just put one zone on one MPI process and let threads, do the part of the work?
Yeah. So for example, in this case, there is a total of 4,096 zones, right?
Yes.
So, so there's different ways. So there's different ways in which the hybrid version it could do it. You could have, for instance, here for the 8192 case, you could have say 4,096 processes, and each one is 2 MPI OpenMP threads, right? Or you could have significantly fewer number of processes, and you can have more threads. But the total number of workers would be using this number of cores. So the idea here is, actually for this one, is taking the best combination that was found in the hybrid version. So it's not necessarily where it used the maximal number of MPI processes, but it found a combination where, given a certain number of OpenMP threads per process, it was able to achieve much better performance. That was the idea. Okay. Yeah.
Can I clarify something? So, as you explained earlier, you reduced the time from 20 units to 11, right?
Yeah.
But now you have 4 threads. I guarantee that those threads of 10 isn't possible that actually they may run in sequence? Are you guaranteed that they are going to run in parallel? You go the first 2 of 10 units and then the next 2 of 1?
So the processing of the zones themselves, they can be done using a parallel for loop. So each one can be processed in parallel by the threads.
2 workers, right?
Yeah.
At a time. So how do you know that you're not going to get 10 and 10 in sequence?
So
you get to 10 and 1, and then another 10 and 1, so eventually the time gets the same.
So each zone is going to be processed in sequence. So the first zone, let's say the larger one, initially took, say, a time of 20 with one process. So now with 2 OpenMP threads, you could potentially cut that in half. So that time would be, instead of going to 20, it processes the first one in, let's say, half the time. And then with the 2 threads, it's able to process the second zone also in half the time.
But you always have this limited number of cores, right?
But that's what I'm getting to.
Exactly. So I mean, when you are doing, let's say you have only 2 cores to do the job. So then it will take, in our example, 20 seconds. One took 20 seconds, the other took 2 seconds. The total time is still 20 seconds. Now, if you're talking about splitting in, 4 threads, then how would those 4 threads work? There are only 2 cores to do the work.
So that's why I was asking whether there's a chance that actually in those 2 cores, you might end up with the threads that you get 20 and 10 and 1.
Yeah.
In the next kind of work, then you are going to get again 10 and 1, and eventually the time gets the same. Or are you actually guaranteed to get 10 and 10 running in parallel and 1 and 1 running in parallel? And then in that case, yes, you reduce the time to just 11 units.
Yeah, so in the example I gave, the assumption I was making was that each of the zones themselves, you would be able to process them using like a parallel for loop, for example. So if you're processing it with, say, instead of each one being processed by 1 thread, each one is being processed now in parallel by 2 threads. I mean, what I mean is that the first zone is being processed by the 2 threads, and then the second zone is being processed by 2 threads, rather than each zone being processed in parallel, each by 1 thread.
So you're guaranteed that you are going to have that particular sequence.
Yes, that's the idea here. Okay. Okay, so that's how, for that particular benchmark, it was able to yield some potential improvements. How the introduction of OpenMP threads into the program could help in the load balancing. So just in summary, there's a number of technological trends which actually makes hybrid programming very important to consider. In your clusters, the nodes are getting larger, fatter, meaning that you're getting more and more cores. And there's also CC-NUMA characteristics, so they're becoming more complicated to program. And as a result, when you're having more and more cores, that's resulting in also less memory available per core. And then also, just in general, with the applications we're dealing with, as we're going to extreme scale, we have to often deal with more dynamic load balancing strategies to actually handle them efficiently. And all these lend themselves to a strategy where you're able to make use of an additional programming model in combination with MPI, where you're able to potentially get some improvements in terms of dynamic load balancing and also in terms of reducing the memory requirements. So with OpenMP, you can potentially develop more memory efficient algorithms within the node. And then you can work share among the different threads using potentially various scheduling policies. It could just be a static schedule, but then you can also use more dynamic schedules as well, potentially, in order to contend with this load imbalance. And then also there's different ways in which you could potentially hide communication latency using OpenMP as well. But then you always add the caveat that for your particular application, just using MPI, it might work perfectly well. So it really requires experimentation to see what are the characteristics of your application and whether you can actually benefit from using OpenMP. Okay, so that's just covering some of that. And now I will continue on to talk a little bit more about just some miscellaneous topics within OpenMP, particularly in dealing with some common programming errors. And then I'll talk a little bit about some performance topics. OK, so what are some very common sources of errors? So believe it or not, one really, really common source of error is just misspelling the construct name. And with Fortran, for instance, this can actually be very difficult to find because the compiler might just treat it as a comment. So if you misspell it, then you may not even receive any sort of feedback from the compiler that you're doing something it doesn't understand. It might just assume that you didn't. It might just ignore it, for example. And then your program won't run correctly, and it can be difficult to figure out what went wrong. So this is actually, it seems kind of simple, but it can actually be tricky to locate. The other issue is wrongly declaring your data attributes. So it was mentioned earlier in the morning that it's a good idea, especially when you're initially developing your application, to use the default none clause. So that kind of forces you to explicitly specify the data scoping for all your variables. And this can force you to actually think about how all the variables should be scoped. And then once you've actually figured out how all the variables should be scoped, then if you want to make the code a little less less verbose, you could remove that. But when you're initially writing your code, it's a good idea to use that. Incorrect use of synchronization constructs can also lead to very subtle errors that can be difficult to find. Oftentimes, if you just stick to the main directives that OpenMP provides and don't try to do anything fancy with flush, for example, you tend to be OK. But the more lower level you try to program with, including using flush or using even locks in some cases, there's issues that can come up there. So you need to be careful with that. Even using this no-wait clause on some of the work-sharing constructs, if you're not careful, that can lead to subtle race conditions. And just generally speaking, race conditions can be very difficult to find. And this is one of the major pitfalls when you're doing shared memory programming is you have to contend with race conditions in your code. And they can be notoriously difficult to locate. There are some tools that can help you to try to track down race conditions. But sometimes, even then, they won't be able to find all of them. So if you recall from the earlier in the morning, with regard to synchronization, really in your memory, OpenMP is a shared memory model, but in actuality, every thread has its own view of shared data. Okay, so if one thread is modifying a particular shared variable, it's not necessarily the case that the other threads are going to immediately see that change. It's not going to be immediately visible to them. So how you actually communicate between threads when you're using shared data, it's not simply a matter of just writing to a flag, for example, and the other thread will see it. To write correct code, you would actually have to do a little more than that. You would have to ensure that some sort of flush operation happened on both sides for the change to be visible to the other thread. And again, this can be done using the higher level OpenMP constructs, like a barrier, for example, that has an implied flush. But if not that, then you'd have to make sure that you're using the lower level constructs correctly. Compiler routinely will reorder instructions So you can't assume that just because you modify two shared variables in a particular order, that another thread is going to see those modifications in the same order. Okay? Compiler is free to change the order, or the hardware can change the order in which the modifications happen. So you have to be aware of that, and then you have to use the flush directive and so forth to enforce ordering. And then the other thing you can make use of is that the compiler, it can't move instructions past like barriers or flushes on all variables. So you can make use of these constructs to kind of ensure that the ordering is correct. So race conditions is just giving what a definition of what I mean by race condition, which is it's just that when several threads are accessing and updating shared data concurrently, and there isn't an appropriate synchronization to enforce an ordering between it. And the user really is expected to write code that doesn't have race conditions. You can't expect the implementation itself to report back to you that, oh, there was a race condition here, or give a very elegant error or a very helpful error at runtime that, oh, there's a race condition, I'm stopping. No, oftentimes instead what will happen is you'll just get some very bizarre results. And even worse, you might get some bizarre results every 1,000 times you run the code, not every time. So that's even worse because it makes it very hard to find. So race conditions can be pretty difficult to locate. And again, it's a matter of following a discipline and how you use these synchronization constructs. And oftentimes, if you're using shared data a lot, sometimes it's helpful to privatize your data, and that will lessen the chances that you will encounter these sort of race conditions. And I mentioned that there are some tools that can help you in detecting data races. So Intel Threat Checker, Threat Analyzer from Oracle. These are some examples of some tools, and there are many others. So just as an example, suppose we have a code here where in a loop, you have a parallel loop here, and you're making a call to this subroutine sub A. And let's suppose that additionally we have this global data, A and B. So you have these two arrays which are global. So within this subroutine sub A, it could, for example, be just doing a write to the B array, not realizing who was calling sub A. So because sub A was called within this context of multiple threads calling it at the same time, and because B is actually global, so it's shared amongst the threads, this ends up being a data race, right? So it can be a tricky data race to find if one person wrote this and a different person wrote that. It could be tricky to find, but this is a data race. So how can you deal with this sort of data race? So one way, so again, this is just illustrating the fact that it's a data race where both threads are basically modifying the same B at the same time. So one way to deal with it would be to just make the array B two-dimensional. So we did something similar to this, if you remember, in the pi example, where we had a sum variable, and then we just promoted that to an array in order so that each thread could be working on a different copy. Well, you could do something similar with B. You can add an extra dimension there, which is sized as the number of threads. So each thread will just be writing to its own particular slice of this B array. So doing this would require actually making a lot of modifications, not just in the declaration, but in all the various uses of B. You'd have to change the code. So it's a lot of work to introduce this sort of change to get rid of a data race, and not necessarily very portable. So instead, you can just use the thread private directive, and this is a much easier way to deal with this sort of issue, where B is a global variable, but the idea is you want each thread to have its own copy of B, to have its own private version of B. And so you can just use the thread private, and then that'll take care of it for you. So now there's no data race anymore just by introducing this directive. So when global data is shared, data races is something you have to be aware of, and it can creep into your code in various ways. So correctly synchronizing your code and being aware of where shared data is being accessed by multiple threads, this is very important. And it's your responsibility to deal with the situation. The implementation isn't going to do it for you. You could generally do it by splitting the data by promoting like some shared data into multiple copies, which are each accessed by different threads. Or you can use the thread private directive, which is often the simpler way to go. So that's just a recap. OK, just a few performance topics. So generally, you want to be aware of overheads that are associated with the different OpenMP constructs in the thread management. So I had mentioned earlier that I provided to you in that tarball some micro benchmarks. So if you haven't gotten a chance to do that, or maybe later today, you can try running some of those just to see how the different OpenMP constructs, what kind of overhead you see associated with them. So that might be very instructive to do that. And those micro benchmarks, by the way, came from EPCC. So one of the general tips is that you don't want to create too many parallel regions. So there's often a cost associated with a parallel region, either in creating the thread team or waking up the threads that might be sleeping. There's a cost and overhead there. So if you can reduce the number of total parallel regions in your code, that could be helpful. So for example, if you can avoid having a loop where you're constantly creating a thread team doing work and then closing the parallel region and then redoing it on the next iteration. If you can avoid doing something like that, that can save you. Another thing to keep in mind, I think someone earlier had asked this question about using dynamic loop schedules. They can actually have much higher overheads compared to static schedules under certain scenarios. So for example, if the amount of work you're dealing with in your loops is very fine grained, then the overhead associated with actually dynamically scheduling the iterations, that can start to overtake the time that's actually being spent within each of the iterations. So using a dynamic loop schedule in that case, that can hurt you. You can vary the chunk size to maybe deal with that, or you can use a guided schedule to deal with that. So that's something to keep in mind. Synchronization can be expensive, so you want to try to minimize synchronization where you can. Use no wait where possible, but again, be aware of possible data races. Privatizing data is another good way to avoid synchronization if you're dealing with private variables and you don't have to synchronize as much. And then also critical regions. If you have critical regions in your code, try to reduce the amount of work that you're doing in a critical region. So that's just a general tip that most of you should be familiar with. You don't want to be having very huge doing a lot of stuff in your critical regions, because then the other threads might just be waiting around doing nothing. Another thing you want to do is choosing the default behavior carefully. So using appropriate schedules for your loops. Which wait policy do you want to use? That can, depending on the type of code you're dealing with, you may want to go with a passive or an active wait policy. So you need to potentially experiment with that. Thread and data affinity is really important. I think this was mentioned a few times. And the thread affinity is dealt with actually in OpenMP 4.0. And even presently, most compilers have ways to kind of specify what kind of affinity you want. For example, with Intel compiler, you can use this KMP affinity. With GNU, you can use GOMP CPU affinity. And different compilers have different ways of doing that. There's no general method for how you can handle data affinity with threads. So you'd have to find some other approach. So one way to do that is to make use of a first touch policy that's often used, where you have your threads are going to first go and access the data. Whichever data they want to use, they'll do an initial access of that data. So that will ensure that the OS assigns the pages to the different threads memories in an efficient manner. There's also tools like there's other tools you can use. TaskSet, NumaCTL, Liquid is another tool that can help you with determining what's the best way of placing your threads and managing the data that it's accessing. Various aspects with regard to the structure and characteristics of your program. So, minimize the sequential part of the program. Of course, you're all familiar with Amdahl's law. This is going to be a bottleneck on how much total speed up you can achieve. So try to reduce this if possible. be aware of and address load balance or load imbalance. Cache utilization and false sharing. This can also kill speed up. I'm going to elaborate a little bit more on that. And then also very large parallel regions. It can actually help reduce overhead. So in addition to not having as much startup cost in actually creating the parallel region and then tearing it down, you can also, by having larger regions, that can also enable more scope for compiler optimization within the region. And it can yield potentially to better cache usage as well. So this is generally a good strategy to try to expand your parallel regions as much as you can. And then the quality of the compiler is also a factor on achievable performance. So OpenMP, unlike some other languages, parallel languages from the past, it's not like a Herculean task to implement it necessarily. So you're not going to necessarily have huge dramatic differences in different good OpenMP implementations. But there are differences that you should be aware of. So just very briefly on OpenMP implementation. So what does it generally do? So you're all probably saw earlier an OpenMP version of the PyCode and a pthreads version of the PyCode. Well, you can sort of think of the OpenMP, the Java implementation, as taking the OpenMP version and trying to create something like the pthread version from it. So oftentimes what the compiler will do is if it sees a parallel region, it'll do what it's called outlining. It'll create a subroutine where the body of that parallel region will essentially be outlined into that subroutine, and sometimes called a microtask. And then in place of that parallel region itself, it'll do some sort of call, like a fork call or something, which will actually be responsible for creating the thread team or waking up the threads, which might be sleeping, for example, to actually execute the body of this microtask. So this is typically how it would work. And then you have a runtime library. In addition to the compiler doing all the translation, you have the runtime library, which is responsible for scheduling loops, scheduling tasks, synchronization, and then in other possible features as well. So each compiler generally has its own runtime support. There is an effort to create a sort of a community OpenMP runtime, which Intel has put forward. That now a lot of people are kind of working around that one. But many compilers have their own custom runtimes, and different runtimes might be optimized for different systems as well. So you should be aware of that. So in terms of data locality, it's obviously a very, very important. And usually what we see with OpenMP is you have this implicit notion of data locality. So each thread is essentially from the programmer's standpoint, there's a shared memory which the threads are accessing. Underneath, threads are fetching data into their local caches, and then they're working off of that much of the time. So what you probably want to do to get good performance is you want to emphasize on privatizing data where possible. That's one way to try to get more control over locality. And then also optimizing your code, for instance, your loops for cache utilization. This can also be a strategy for getting better locality. And then also, as I had mentioned, on NUMA systems or CC NUMA systems, typically you have a first touch policy, so making use of that to place the data where near the threads that are accessing it. This is an important thing to try to do. And then also, if you're dealing with shared data, you want to try to privatize data where possible, and you also want to be careful about how the shared data is laid out in memory, because this can cause serious performance issues. And then I'll mention that in a few slides down. Okay, so critical regions, as I had mentioned a little earlier, if you have very large critical sections in your code, if it's possible to reduce the size of them, this can be helpful. So if it's possible to do these updates, for instance, in 2 different critical sections, you'd want to do that. And this is just another example where, again, if it's possible to try to reduce the amount of work that's being done in a single critical section and maybe use multiple of them, you should try to make use of those sorts of transformations in your code. Implicit barriers are another thing to consider. So most of the OpenMP constructs, work-sharing constructs, they make use of implicit barriers. And so if you have, for instance, an OMP4 followed by another OMP4, and you can determine, for instance, that there isn't a need for this barrier, you want to try to make use of the no-wait clause, for example, to eliminate that barrier. And that can save you quite a lot. So here are two cases where you can actually utilize the no-wait clause because a barrier wasn't necessary. Here, for example, you see two consecutive loop nests. The first one is modifying D, which is not being used at all here, and they're not both modifying the same variable. So these are independent sections of code. You can do a no-wait here, and it'll work fine. Here you see that there actually is a dependence. So what's being written to D here is also being used here. But you can still use a no-wait here. And the reason for that is because in both cases, if assuming that there's a static schedule being used, and by default, in this case, let's suppose there is, then the spec will guarantee that the iteration to thread mapping is identical in both cases because the loop bounds are the same. And if the schedule is the same, the loop bounds are the same. They're both using a static schedule. You can assume that the iteration of thread mapping is the same, which means that as soon as the threads have completed the iterations here, they can move on to execute the iterations here, and it's fine. So, okay, this is a diagram I think that you're already familiar with a shared memory system. In fact, you have to deal with different cores have their own caches. And you come up with this issue, which is a very common performance issue often with shared memory programming, where you have different cores that are updating data. And the data themselves actually, they're different data objects in memory, but they're on the same cache line. So this can be an issue because if you have multiple cores that are making modifications to the same cache line, that can cause invalidations on both sides. So this can lead to significant performance degradation if you're not careful. So here was an example of a code that someone in our group had taken a look at some years back, where actually it was observed comparing the OpenMP version to the MPI version. There was huge overheads in one of the subroutines in particular. It was found to be, almost 9 times lower than the MPI version just because of this particular subroutine. And so when you took a look to see actually what was going on, you found that within the subroutine, these lower and upper bounds of these arrays, which were actually used privately by the threads, were shared. So what I mean by that is basically the array itself was replicated, so each thread had its own copy. But many of these copies were actually residing on the same cache line. So whenever these different threads were accessing these arrays, it was causing a huge number of cache invalidations, and that was really hurting performance. So this is a situation where simply managing the data layout in a way that's more sensitive to what's going on behind the scenes, that had a big impact, and that was able to reduce the performance overhead significantly. And then there's another example where we had someone who took some codes from the Phoenix benchmark suites, which was written in P threads, and he ported it to OpenMP, and he was analyzing these codes, and he found that 5 out of the 10 appeared to be having some issue with huge amount of cache invalidations, and as a result, he wasn't getting good speed up. Just going from 1 to 8 threads, so we're not talking about trying to get speed up over a huge number of threads, just a modest number of threads, but he wasn't able to get good speed up. And he saw that it was because the lack of speed up was correlated with the high cache invalidation counts. So he used this tool he developed to try to identify which of the variables were being accessed, which could be contributing to this. And he isolated which variables were being accessed in the different benchmarks, which were contributing to these cache invalidations. And he saw, when he looked at the code, that there was a false sharing issue. So he adjusted the data layout, and by doing that, he was able to get much better speedups for the codes which exhibited this issue. At least for these 2 codes, you can see there was a major improvement in the speedups. And also in this one, he saw some improvement. And this one, he still wasn't able to get speed up, but it was at least better than what he was getting before. The reverse index didn't really show any of this issue at all, so it didn't change at all. But again, this is just another illustration of how false sharing is something you need to be cognizant of when you're looking at your codes. And so you need to think about data layouts to try to mitigate this particular problem. OK, so in summary, OpenMP, it's designed to be very easy to use. But there are some issues that you have to contend with in order to get really good performance out of it. And again, that's what we're all here to do, is to learn about how to get really good performance from our programming models. So data races are a common programming error. So if you need to be able to contend with that. And one good way to deal with that is to privatize your data, so to reduce the amount of shared memory you're using. You won't need to be aware of possible subtle synchronization errors that can creep up into your codes. So sticking to some common OpenMP directives is one way to deal with that. There's also, you should be very aware of the different overheads associated with the constructs you're using, be it creating a parallel region or the reduction, for example, and barriers, all these sort of constructs which you might find commonly in your codes. You should be aware of what kind of overheads are associated with those constructs. And you can use micro benchmarks to help you identify that. You need to find the particular documentation for your implementation and/or system to control data and thread placement, because this can be vitally important for performance. And also false sharing, it can really kill your performance if you're not aware of that as well. So you need to consider that and think about data layout in order to reduce this issue. And I think that's all. Is there any questions? Yeah.
When we measure the false sharing, then we know the size of false sharing that we have in our implementation.
Right, yeah. So there are tools that you can use to, for instance, look at performance counters where it'll tell you like how many cache invalidations that are being caused by your code. So if you see, for instance, so what he observed is he used these tools and he was able to see huge spikes in the cache invalidations, and in particular when he was accessing particular sections of the code. So this was a sign that something was going on. And so when he examined the code, he's able to very quickly isolate what were the particular memory accesses which were causing these issues. So that's the way that he went about identifying it. And there are tools, I think, that I don't know the names off the top of my head, but I think there are some tools that are being worked on to help find these.
So in order to check the number of cache misses?
Well, it could be cache misses, but cache invalidations. Like on a given particular memory access, if there's a huge spike in the cache invalidations, that could be a sign that that issue is coming up.